Okay, so good morning, everyone. Welcome back to Math 115. So homework 8.4 is due today. Quiz 1 is today. If you're watching the recording and you didn't know that there was a quiz, well, you better email me. Office hours may be changing. I just pulled the class, and it seems like a lot of people have a conflict, so I might end up changing those. So be on the lookout for an announcement about that. Okay, so let me quickly remind you what we were doing last time. So last time we started section A.4, and A.4 was all about radicals and rational exponents, and we got through most of the radical stuff. We're going to finish rational exponents today and maybe touch on A.6. So what we were talking about was, first we just discussed square roots, and of course every positive real number has two of them. One is the positive square root, and one is the negative square root. And another word we use for the positive square root is the principal square root. So the principal square root is always the positive one. So the reason we care about this principal square root is later when we talk about functions, we want the square root function to pass the vertical line test. And if we include both of the square roots in the function, then it certainly will not pass the vertical line test. So we saw some basic properties of square roots. The most important ones probably are the fact that if we have the square root of two things being multiplied, we can separate that out as the two square roots being multiplied. Same deal with division. If you know that division is just fancy multiplication, then you can just use this rule to show that this fraction rule should be true. So then we talked about nth roots, or higher order roots. So we want numbers such that if we multiply them together n times, n many times, so n could be like 5 or 6 or something like that, then we get a. So an nth root is a number such that if I take that number to the power n, I get back a. And the only tricky thing about nth roots is there's a big difference between odd roots and even roots. Who can tell me what is the trouble or the potential trouble with taking even roots that we don't have to worry about when we're doing odd roots? Negatives, right? I cannot take an even-powered root of a negative number, right? But I can take an odd-powered root of a negative number. So that's one of the things we want to be on the lookout for. So we saw some properties of nth roots. They're pretty much the same as the properties of square roots. Namely, if I take the nth root and then I do the nth power, I get back what I started with. If I take the nth power and then take the nth root, then things get a little bit hairier. I need to be careful about whether the power is even or odd, because if the power is even and a was a negative number, then a to that power would be a positive number. If we take the even-powered root of a positive number, if it's the principal root, we get back that number as a positive. So we have to be careful if a is negative when we're doing even roots and even powers. Okay, so 5 and 6 are the only real new ones about the nth root, which is that, okay, the nth root of the mth power is the same as the mth power of the nth root. Okay, that makes sense. And if I take the mth root of the nth root, which is kind of hard to say, then I get the m times nth root. And that's going to make a lot of sense in a minute when we talk about rational exponents. Okay, so then we talked about simplifying roots. So simplifying roots was as simple as expressing the number inside, okay, as powers of numbers. And we can always take out of a root any power of a number which is a multiple of that root. So in this case, we rewrote 4 to the 16 as 4 to the 15 times 4. Since 15 is a multiple of 3, it can come out of the root as a 4 to the power 5. Okay, so when the 15 comes out, the 15th power comes out, then what we do is we divide that power by the root. Okay, so that was what we did. And then the last thing we did was we tried some practice with the partner. And then I think we were done. So, have there been any questions from anyone in the class? Maybe if you looked at the homework or something and you got a little confused. Any questions that we should discuss before we move on to new material today?
We do a couple more of these, like, complex.
Yeah, we can do a couple more simplification problems. All right, let's just do a quick couple in succession here. So let's try maybe the square root of 250. Okay, so sometimes what I like to do when I'm doing extra practice like this is ask for a student to help me walk through how I should start this problem, and we can go step by step. So what's the first thing that I should do if I want to simplify the square root of 250? Sorry? Yeah, find multiples of 250. I want to rewrite 250 as a product, basically. So I'm going to rewrite 250 as, what would be a good way to rewrite it? Okay, let's see two possible examples. One example, I'm going to rewrite it as 125 times 2. And the other example, I'm going to rewrite it as 25 times 10. Which one do we like better? 25 times 10. I like 25 times 10 better. Why is that better than 125 times 2? Because 25 is a perfect square. I can rewrite 25 as 5 squared, right? So, sorry, was there a question? Okay, so I can rewrite 25 as 5 squared, and by the rule which says that if I multiply two things together, that's just going to be the square root of one times the square root of the other. And I know exactly what the square root of 5 squared is. What is it? It's 5. Okay, that's fine. If you want to do it another way, let's see how, if you had accidentally set it up this way, for example, because you didn't see that you could set it up in a smarter way, then you could just rewrite this. 125 is 5 cubed. So you could rewrite this as the square root of 5 cubed times 2, which is the square root of 5 squared, times 5 times 2, which is, of course, 5 times the square root of 5 times 2, which is, of course, 5 root 10. The reason we know we can't pull anything else out of something like the square root of 10 is because the 10 is a product of primes. So there's no square factors of 10. Okay, how do you feel about that? Any questions on that one? Okay, let's do a more complicated one. Let's do the cube root of 81x to the 4th divided by y to the 9th. All right, is that complicated enough? Why don't we make it even more complicated and make it negative? All right. All right, well, I want you to see a bit of everything in this problem. Okay, so let's see how we should start this problem. So the first thing that I'm going to do is recognize that this is a cube root of a fraction, okay? The cube root of a fraction is always equal to the cube root of the top divided by the cube root of the bottom. Now, I can rewrite the bottom immediately. as what? How can I rewrite the bottom? I can rewrite the bottom as y cubed. Okay, I take the power of 9. It's coming out of a cube root, so I divide 9 by 3, and I am left with 3 powers of y. Okay? The other way you can think about that is if I did y cubed times y cubed times y cubed, I would get y to the 9, right? Okay. How about the top? Someone help me rewrite what is underneath on the top in a smart way.
Cube root of -3 cubed, and then you just put the x into a different fashion.
Well, 81 is 9 times 9, right? Which would be 3 to the power 4, right? So I can rewrite this as negative 3 to the power 4 times x to the 4. Okay, and now I can rewrite this as the cube root of negative 3. I'm going to put the negative inside and then cube that and then multiply by 3, right? Because what would happen here? Negative 3 cubed, I would get negative 3 times negative 3, which is 9, times negative 3 one more time, which would be negative 27, right? And then if I multiply negative 27 times 3, I would get negative 81, right? Okay, times x cubed times x. Now what can come out? I can pull out the negative 3. What else can come out? X. And what am I left with inside of my cube root?
3x.
3x. Very good. And then all divided by y cubed. All right. So not so bad. Another way you could have done that, by the way, is you could have instead said that negative 3 to the 4th power is the same as negative 1 cubed times 3 to the 4th. That's another way you could have said it. And then you could have taken out the negative 1 and then taken out 3 cubed and so on. So that's another method. There's lots of different ways that you can skin a cat. Not that anyone would ever do such a thing. Okay, so I think that's all the time I can spend on examples for that. If you want to see more, schedule an appointment with me if you can't make it to office hours. All right, so now I want to talk about something new, which is combining like terms. Not combining like terms, sorry, it's adding radicals. And the method we're going to use to add radicals is we're going to combine like terms. So just like before, okay, when I had to deal with something like 2x squared plus 3x minus x squared plus 4x, what did I do? I looked for all of the terms that have the same power of x, right? And I add those ones together because those are like terms. Okay, so this one, and this one are like terms. Similarly, when I am doing square roots, like terms is going to mean terms which have the same number under the square root. Okay, for example, I can add together the root of 2 plus 3 times the root of 2 to get 4 times the root of 2. It's like if I had one Beanie Baby and I added it to my collection of 3 Beanie Babies, then I would have 4 Beanie Babies, right? Okay, so this is what we mean by like terms. Okay, so one thing that we can't do is add something like the square root of 2 plus the square root of 3, right? These are not like terms. Okay, so I can't combine them. Why are they not like terms? They are not like terms because they need to have the same number under the radicand, okay? So a mistake that I see very, very often in 115 is that on a homework or a quiz, a student will see something like this, and they'll say, aha, square root of 5. But that's not actually true. The square root of 2 and the square root of 3 do not sum to the square root of 5, in fact. Okay, so this is what we call a nonlinear relationship, or a nonlinear function, which I guess we still don't know what functions are, but we'll get there. So, we cannot add these. So let me be emphatically clear that this is not equal to the square root of 5. Exclamation point. Okay, so let's do some simplification. Well, can I combine these? I've got a square root 45 and a square root 20. No, they're different square roots. But there is something that I could do first that might help us to eventually add them together. And that is to simplify. Okay? So I'm going to take 2 steps here. One is simplify roots. And 2 is combine like terms. All right. So first of all, how can I simplify the square root of 45? Let's get a little faster. Well, I don't always have to write out the fact that 45 is the product of 9 and 5. Okay, I can just say, well, I know that 45 is 9 times 5. I pull the 9 out as a 3, and I'm left with a 5 inside. If you practice, you'll get fast like that as well. But if you want to ever see what I have done here in more detail, then please just raise your hand. Okay, 20 splits as what and what? 4 and 5, right? And 4 is a perfect square, so it can come out as a 2. So I'm left with a plus what? 14 root 5. Am I done? No, I can take one more step. 17 root 5. Very good. Okay, so I can simplify all the roots, and then if there are like terms, then I can combine them. Any questions on how to simplify sums of roots? Again, sums I think are more difficult than products.
How'd you get 14 again? I'm so confused on that.
Okay, so how do I get 14? Let's draw out the work here. So I wrote 7 root 20 as 7 times the square root of 4 times 5, which I rewrote as 7 times the square root of 4 times the square root of 5, which is the same as 7 times 2 times the square root of 5. So since 7 times 2 is 14, I get 14 times the square root of 5. Does that make it clear? All right. Any other questions? All right. Then let's move on to rationalizing the denominator. Okay, so just like there's like social etiquette in the real world, there's also a sort of mathematical etiquette in terms of proper ways to simplify things. And one of the things that someone very long ago decided was improper was to have square roots or any kind of root in the denominator. So they came up with this process called rationalizing the denominator, which is a method by which we are going to make the denominator rational, because oftentimes the square root of a prime number is going to be, well, actually always the square root of a prime number is going to be an irrational number. We don't like irrational numbers in our denominator, so we're going to make it rational by doing the following. I can take my a divided by the square root of b, and I can multiply on the top and bottom by the square root of b. I haven't changed anything if I do that. And on the bottom, I get the square root of b squared, right? So this is a root b over root b squared. What do I get when I take the square root of something and then square it? I get whatever that number was. So I get a square root b divided by b. Simple as that. Okay. Now there's a little bit more complicated one written down here. Well, first of all, do we have questions about how we just did this? All I did was multiply by 1, but it is kind of confusing the first time you see it. All right, no questions, then we're going to move on to something a little harder. Okay, so this one is tricky. I can't use my same trick here. If I try to multiply the top and bottom by square root of b, what's going to happen is I'm going to get a root b on the top, and on the bottom, I have to distribute, right? So I'm going to get root b plus b. Ah, crap. Okay, so I still have a square root. Maybe if I just do it a couple more times, I don't know. But no, it's not going to work because this is a half power, or this is a square root, and this is not a square root. So if I multiply again, then I'll take care of this one, but then this one will become a root again. So that's not what I want. But there is actually a clever trick that we can use to handle this. Does anybody know what it is?
Multiply by 1 minus root b.
Very good. We need to multiply by 1 minus the square root of b. Does anybody know the fancy math word for that? 1 minus the square root of b has a special relationship with the expression 1 plus the square root of b. They are called, I think I heard it, conjugates. They are conjugates. So we say we multiply by the conjugate. Okay, or we call 1 minus square root b and 1 plus square root b conjugate pairs. Okay, so what's special about conjugate pairs is that the top is going to become a minus a root b, no problem. What's going to happen on the bottom is we're going to FOIL. And the cool thing about when we FOIL something with a plus and with a minus is that the middle terms are going to cancel. So we're going to get 1 for the f. For the o, we get minus square root b. For the I, we get plus square root b. And then for the L, we get minus the square root of b squared. So since we are subtracting a square root of b and then adding a square root of b, those cancel, and we're left with just a minus a root b in the top, and in the bottom I have 1 minus b. Okay, so you can think of this as like a reverse difference of squares, okay? So if I assumed that b was a square number, then 1 minus b, I would factor it as 1 plus the square root of b and 1 minus the square root of b, right? So if I do difference of squares in reverse, then I can take these factors and then they're going to multiply together into something which has the square of the second term here. Okay. So that's called multiplying by the conjugate. So that's one way that we can rationalize the denominator if the denominator is caught up, or if the irrational part of the denominator is caught up inside of a sum. Okay, let me ask a quick question. Why can I not just do the following? Why can't I just take rewrite this fraction as a divided by 1 plus a divided by the square root of b, and then just rationalize this one? Why can't I do that? Because it wouldn't be equivalent. This is not the same thing as this, right? I can only break up fractions like that when there is a sum in the numerator. If there's a sum in the denominator, this is what we would call a big no-no, meaning that we can't do it. I mean, you can, it's just it won't be correct. So this is something that I like to show people, like common mistakes, so that they're aware of them, and if they see themselves making the mistake, then maybe they'll remember, like, wait, wasn't that something that he told us not to do? Anyways. Okay, so let's see a quick example here. Let's rationalize the denominator. We've got a divided by the cube. We got the cube root of a divided by 4b to the power 4. All right. So the first thing I'm going to do is I'm going to rewrite as the cube root of a divided by the cube root of 4b to the power 4. Okay, and now can I pull anything out of any of these roots? The top I can't simplify any further. How about the bottom? I can take b out, right? So I take a cube root of a, and I divide that by b times the cube root of what? 4 what? B. Very good. 4b. So I rewrote b to the 4th as b cubed times b, right? And then I took the b cubed out, so I have a b left inside. All right, now what should I do to rationalize this? Well, I have a cube root of something in the denominator, but it's not in a sum, so I don't need to multiply by the conjugate. What was the first method that we used before conjugate? I'm going to multiply the top and bottom by not the whole denominator, but just the root part of the denominator. So I'm going to multiply top and bottom by cube root of 4b. Actually, I'm going to multiply times the cube root of 4b twice. Why twice? Because it's a cube root, and I want 3 total multiplications in the denominator in order to get rid of it. Okay, so what do I get? I get the cube root of a times the cube root of 4b squared divided by b times what? Cube root of 4b cubed, right? Because I already had a cube root of 4b in the original denominator. So what is the cube root of 4b if I cube that all? Just 4b. Okay, so I get b times 4b. So in the end, I get cube root of a times the cube root of 4b all squared divided by 4b squared. Okay, now the denominator looks nice. Great. Any questions on this example?
For test and quizzes, will we have to make sure that there's no square root in the denominator? Like they'll take off points if we want.
Yes, you should rationalize the denominator unless the problem doesn't specify that you need to simplify completely. Usually what I'll write on a quiz will be, I'll give you the problem and I'll say like, do this operation, and then I'll say, simplify your answer completely, or I won't. Or I'll say something like, you can leave your answer in however you like. Something like that. But yeah, well, okay. I don't want to say that. For now, let's always rationalize the denominator until otherwise specified. How about that? Okay. One thing I want to do here is make sure I set an alarm so I don't forget to start the quiz when it needs to be started. Okay, so that's rationalizing the denominator. Any other questions on this example? So the question was, do I always need to rationalize the denominator on a quiz or a test? The answer is yes for now. There will maybe be some circumstances later on where I won't require you to do that, but I'll always say so. Okay, it doesn't seem like there's any other questions, so let's move on to rational exponents. Okay, God, I have been dancing around rational exponents this whole time. It's really kind of strange to me to talk about all of these square roots and nth roots without talking about rational exponents, so I'm glad we're here. So what are they? Well, rational, right? What does that word mean again? It means ratio, which means we're talking about fractions, right? Okay, so we're going to have powers that are a fraction, okay? Something like 1 over n or m over n, where m and n are, of course, going to be integers, right? Because m and n need to be integers in order for this number to be a rational number, which is the type of exponent that we're specifying. Okay, so this is the cool relationship between these is that x to the power 1 over n is defined to be the nth root of x. Okay, so 1 over n power is the same as nth root of x. In other words, the square root of 2 is the same as 2 to the 1/2 power. Okay? All right. We also have x to the power m over n, okay, is equal to x to the power m to the power 1 over n. Why? Because when we have something with a power to another power, what do I do with those powers? You multiply them, right? So if I multiply m times 1 over n, I get m over n, right? Okay, and this is also equal to if I did 1 over n first, right? Because 1 over n times m is the same as m times 1 over n. And likewise, these two are equal to their root form, which is the nth root of x to the power m, or also the nth root of x all to the power m. So this is how we define rational exponents, and a lot of the time it's easier to express everything in terms of rational exponents than it is to express things in terms of square roots or nth roots, just because it gets really hairy when we have to do things like this. It's easier to write x to the m over n than it is to write the nth root of x to the m, in my opinion. I think x to the m over n is a lot cleaner and easier to see what we're supposed to do. Okay, so let's have a quick note on negatives. Okay, so a quick note on negatives is that we cannot do, we cannot do an even-powered root of a negative number, which a 1/2 power is an even-powered root. It's a square root, right? So sometimes we're going to see things written like so, -1 to the power 1/2. But what we need to remember here is good old PEMDAS, right, which says that I apply the exponent first, okay? So if I do -1 to the power half like shown, I do 1 to the power 1/2, which would be the square root of 1, which is 1, and then I make it negative, okay? So this is a crucial thing here. I think if you're confused about it, it's useful to just always use the parentheses so that you remember whether or not you need to be doing this. Because if you write something like this, sometimes students will rewrite this thing here like this thing, and then they get confused and forget to basically take that negative into account. Okay, so that's negatives. So let's see some quick examples. Okay, how do we actually do fractional powers? Well, the way we do fractional powers is basically to rewrite them in the following way. I'm going to rewrite this as something like 8 squared to the 1/3 power, or I could rewrite it as 8 to the 1/3 power squared, right? So if I want to do this, basically I need to square and take a cubed root. It doesn't matter what order I do it in. Well, I think for this one it's probably easiest to do the cube root first. The reason I think it's easiest to do the cube root first is because 8 has a really nice cube root. What is the cube root of 8? It's 2, because I multiplied 2 times 2 times 2. That gets me 8. Okay, so 2 is the cube root of 8. So I'm supposed to take the cube root of 8, which is 2, and then I'm supposed to square that number and get 4. Okay? Or if you want to go the other way, you could also say this is 64 to the 1/3 power. And if you know that the cube root of 64 is 4, then great. All right, let's do a more complicated one. Negative 16 to the 5/2. I'm a little bit scared here. I'm scared because I got a negative number and I'm doing an even-powered root. So what do we think? No solution? Can we do this one or not? I'm leading the witness here. We can do this one, right? I could not do this one if it was something like this, right? If I had parentheses, but I don't. So the negative doesn't matter. I'm going to do this thing first, and then I'm going to apply the negative sign. Okay, so this is the same as negative, and then parentheses. Which one do we want to do first, the square root or the 5th power? I think square root's easiest to do first because 16 is a perfect square, right? So I can rewrite this as the square root of 16 all being taken to the 5th power, which is negative 4 to the 5th, which is whatever that is. It's 2 to the 10. Something like a million, maybe. All right, so that's how we could do that. I don't know. I guess I should have made this easier to simplify. Any questions on these two examples of how we actually compute fractional roots? All right, so the methodology here is or fractional powers is what I meant to say, not fractional roots. So the methodology here is to basically rewrite it as a power of something to a root, or a root of something to a power. Those are the two methods that we can use. Okay, so let's try a little bit of practice with a partner. We want to do our best to simplify these as much as possible. So make sure we're using our rules of exponents. And let's see if we can get these simplified to least terms. And I'll come around and help if you need a little help with your group. So I could rewrite it right as a 10 times x to the 1/3 times x to the 1/4. If I were to do something multiply something like x squared times x cubed. Well, I'm taking x squared and cubing it, then I'm multiplying the powers, right? But if I take two different powers, yeah, okay. Maybe I can. So So that's something where
That's all I can do.
right? Then in this case, I'm going to multiply those to get x to the 6. So the rule for if I do x squared minus x cubed, so what do I do with the powers? Not multiply, but add, right? I get x to the 5th. So if I do x to the 1/3 times x to the 1/4, what am I going to do with the powers? I need to add them to how to find a common denominator. Yeah, sure.
Sorry, it's is like,
Well, we don't want to continue this form because following this. If we take our expression, what we're supposed to do is right? So in the end, whatever we have should still be the same thing until we start to right? So I can use this because then I would be changing the expression or potentially using the expression. So what I need to do is actually, I'm going to rewrite this. I can do multiplication in any order that I want, right? So 2 times x to the 1/3 times 5 times x to the 1/4 could be rewritten as 2 times 5, right? 2 times 5 times x to the 1/3 times x to the 1/4. Okay, so then you rewrite this as 2 times 5 times 10, right? Okay, now we can simplify x to a certain power times x to another power, right? Okay, I think here's on the right track, but let's just take something really simple like the following.
Yes,
I'm gonna write the marks. Is that okay? Okay, if I were to multiply x squared times x cubed, how would I do it? Add the powers, right? So x to the 1/3 times x to the 1/4, same exact deal, right? It is 2 different powers of x. What do I need to do with the powers? I need to add the powers. How do I add 1/3 to 1/4?
thank you.
Yeah, no problem. I'm gonna go check on some other students, but keep working. Hey. Okay, so we have a negative power in the top, right? So we had a rule named so we had a rule, right? Which said that x to the negative a would be using 1/x3a. That was how we get rid of the negative powers. They go to the denominator as a positive power. So I can rewrite this as what? 21 divided by 7x to the 1/5 times x to the 2/5. Right? Now how do I combine these two? Yeah, you add the powers. Sure, so we can multiply in any order that we want, right? So we could do 2 times 5 times x to the 1/3 times x to the 1/4. Can you write that for me? X to the 1/3 times x to the 1/4. So you can get rid of this x there. So 2 times 5 there. Okay, so now 2 times 5 is 10. Okay, and how do I combine x to the 1/3 and x to the 1/4? We don't want to change the expression, so we don't want to do that. But let's just say I have x to a certain power and x to another power. If I multiply them together, can I write it as x to a single power? Yeah, what should that power be? It's going to have something to do with these 2 powers, right? What should I do? Not multiply, but not divide, but add. In case of multiplication, we want to add the powers. So 1/3 plus 1/4, how do I do that? Yeah, gotta find the common denominator. Yeah. I am.
Solving those questions. So do you know, like, which direction it goes?
Okay, sure. So I think, yeah, it's a little confusing. We were just talking about roots. But in this case, okay, one way we can simplify this, right, is I can rewrite it. We can do multiplication in any order that we want, right? So let's say I gave you something a little simpler, something like 2x being multiplied by 3x. How would I multiply these two together? Well, not distributive property, because distributive is for plus, right? So what I would do is I'd take the 2 times 2 and get 6, and then I take the x times the x and get x squared, right? Okay, so in other words, I can do multiplication in any order I want. I can do 2 times 3 times x times x, right? Same deal here, I can do 2 times 5 times x to the 1/3 times x to the 1/4, right? So this would be 10 times, and then what happens with these two? Can I combine them? There was a rule that we learned at one point that said x to the a, you multiply x to the a times x to the b. What do we get? So say, for example, like x squared times x cubed. What do I do with those powers? You add them, right? X to the 7. So if I have x to the 1/3 times x to the 1/4, I'm going to use the same exact rule, right? I'm going to get x to the a plus b. So how do I do that? I'm going to get x to the, I need to add 1/3 and 1/4, right? That's right, so we just need to figure out how to add 1/3 and 1/4, right? Which is find a common denominator, which means multiply 1/3 times 4 on the top and bottom, right? Multiply 1/4 times 3 on the top and bottom, and add. All right, let's come back together as a group. I want to have a couple minutes to discuss these examples before we move on to the quiz. So this first one here, okay, all we want to do is simplify these down into least terms. So the only thing that's really confusing here, I think, is the fact that we have a 1/3 power and a 1/4 power and not something like a 3rd power and a 4th power. So let's start with something easier than this. How would we simplify something like 2x cubed times 5x to the 4th? How would we simplify that? Well, I would just take the number times the number, right, and get 10, and then I would take the powers of x, which I've got 3 of them here and 4 of them here. So what should I do, multiply or add? Add in this case, so I would get 10x to the 7, right? Okay, so this is nothing different. The only thing different here is that the powers are fractions, okay? So what am I supposed to do? I can rewrite this as, I can do multiplication in any order that I want. So I'm going to do 2 times 5 first, and then I'm going to multiply x to the 1/3 times x to the 1/4. And 2 times 5 is 10. And then, oh God, I have fractional powers being multiplied together. Okay, nobody panic. We're just going to use the same rule as always, which is the fact that if I take x to a certain power a, and I multiply that times x to a certain power with b, I add the powers. I get x to the a plus b. So I'm going to rewrite this as 10 times x to the 1/3 plus 1/4. How do I do 1/3 plus 1/4? Find a common denominator. I get 10x to the 4/12 plus 3/12, right? Which is 10x to the 7/12. Any questions on that one? All right, so I included this one in here because, a lot of students struggle, I find, with applying regular exponent rules. Like, we didn't use anything special here, just x to the a times x to the b equals x to the a plus b. But for some reason, the wires get crossed when we have fractional powers. So I just wanted to give that one as an example. All right. Sorry, what's up? Do we end here? Yeah, I would say that this is least terms. We've combined everything that can be combined in terms of constants, and we've combined everything that can be combined in terms of x. 7/12 is a pretty is a fully simplified fraction. If you wanted to rewrite it as like the 10 times the 12th root of x to the 7, I guess you could. But I think that this already means that, right? That's what the definition is. So I think that that's probably where I would leave it. Good question. Any other questions? All right, then let's talk about the next one. This one's more complicated, except for the fact that I can do multiplication and division in any order that I want, right? So first of all, I could rewrite this as 21 over 7 times x to the negative 2/3 over x to the 1/5, right? And 21 over 7 is just 3, right? Okay, so how do I deal with x to the negative 2/3 divided by x to the 1/5? Well, the negative power here, what should happen to it? It goes to the bottom, right? So this is the same as 3 times 1 divided by x to the 1/5 times x to the 2/3, right? And then that's 3 times 1 over x to the, what? We would get 3 over 15 and then 10 over 15. So they would add together to 13 over 15, right? I think I did that right. So that's just 3 divided by x to the 13 over 15.
Wait, wouldn't you
Have to.
take another root on the bottom?
Yeah, that's a great point. We do have a root on the bottom, don't we? What do we have? We have 3 divided by the 15th root of x to the power 13. How do I rationalize the denominator now? Well, I'm missing 2 powers of x here. So I'm going to multiply by the 15th root of x squared. Why? Because then x to the 13 times x to the squared is x to the 15. So I would get in the bottom just x. And in the top, I have 3 times x to the, well, I could get 3 times the 15th root of x squared. You're right. Technically, we should rationalize that denominator. Very good, Connor. Okay. Final questions on this one before we start the quiz? Sorry? Zoom in, yes. Okay, if you're done taking notes, then please put everything away except for a sheet of paper and a pencil. So if you have a cell phone or a laptop out on your desk, please put it away in your backpack or under your desk or something. If you're wearing an Apple Watch or any other kind of smart device that attaches to any part of your body that uses the internet, then please remove it. If you don't have paper or pencil, maybe try to borrow one from your neighbor. Yeah, what's up? A1, A2, well, not yesterday and not today. Okay, have we gotten everything put away sufficiently? And everyone has a piece of paper and a pencil? Okay, I'm going to put the quiz on the screen. Usually later in the semester I'll bring pieces of paper. But okay,